All right, we'll now take a look at the Bayes classifier and the naive Bayes classifier. The There are a couple chapters or there's a chapter in this textbook, a first course in machine learning, which is an excellent textbook, but unfortunately it's not free, and I felt bad trying to say you should buy this book for just one chapter. So I'll try to find some other relevant resources for you guys here. So anyway, the Bayes classifier is another classification method, okay? Unlike logistic regression, we can use it for making predictions for categorical variables with more than just two classes. So not just is it in this category or not. We can say it belongs to one of multiple classes, okay? It is a probabilistic classifier, okay, very much like logistic regression. So logistic regression will make a prediction with a probability that it belongs to a class or not. And similarly, the Bayes classifier will do the same as well. It's going to say the probability that belongs to this class is this, the probability that belongs to this class is this, and the probability that belongs to the other class is this. Okay, so it is a probabilistic classifier, and so if you have three categories, it might say it belongs to probability class A with probability 0.19, class B with probability 0.8, and class C with probability 0.01. Okay, so everything has to add up to 1. All right, whereas logistic regression would say something like it's either class A with probability 0.19 or not class A with probability 0.81. Okay. Later on, we'll look at KNN, which does non-probabilistic rules. It is a non-probabilistic classifier and uses kind of hard rules as far as making the prediction as to whether something belongs to a certain class or not. Okay, just one note clarification here. It's called the Bayes classifier, and it uses Bayes' rule, okay, but we would not consider it to be a Bayesian statistics method at this point, okay? We're still using kind of frequentist or maximum likelihood methods for parameter estimation. So that's just a side note. Later on, we'll look at Bayesian statistics in probably weeks 8 and 9 of our class. All right. So if you recall your rules of probability, so if you think back to your intro probability or intro stats class, you should have encountered something called Bayes' rule, okay, which says that the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. All right, and so I'm not sure how much probability you guys have had, but the probability of A given B is the probability of something if we know that B has happened. Okay, so for example, the probability of like if you have a regular deck of cards, there's 4 suits and they all show up with equal probability, and so the probability of drawing hearts before you know anything else is going to be 1 in 4. However, if I tell you that the card is red, then it eliminates all of the black cards. Okay, so if you know that the card is red, and there's only 2 red suits, hearts and diamonds, and so the probability of getting a heart, if we know that it is red, is going to be 1 in 5. So the probability of hearts before we know anything is just 0.1 in 4. The probability of it being red if we know that it is, the probability of it being hearts if we know that it is red is going to be 1 in 2. Okay, so that's what we have here. Okay, the probability of A given B. So this is, I guess I'll just kind of write this out here. Sure, go ahead and save that. So this is a little bit silly. So we'll say A is card is hearts, and B is the card is red. Okay, so the probability of A is just the probability that the card is hearts, and that's going to be 1/4. Okay, the probability of B is the card is red, and half of the cards in the deck are red, so we're going to just say 1/2. Okay, and the probability of A given B is the probability of the card being hearts is hearts given, basically, if we know the card is red. Okay, and that's going to be 1/2. All right, we can kind of fill out all of these things. The probability of B given A, this is the probability the card is red given it is a heart. Okay, and that's going to be 1. Every single card that is a heart is red, and so what's the probability that the card is red if we know that it's a heart? That's going to be 1. And so, so this just kind of supports the probability of A given B, which we know is 1/2, can also be found this way. Probability of B given A times the probability of A divided by the probability of B. Probability of B given A is 1 times the probability of A, which is 1/4, divided by the probability of B, which is 1/2. We got 1/4 divided by 1/2, and this is also 1/2. Okay, and that's Bayes' rule. We're just saying that the probability of A given B can be found this way. Okay, and this is useful for us if it's difficult to find this directly. If we know these other probabilities, we can kind of combine them like this and get this value. Right? The probability of B given A times the probability of A is the probability of B and A, and these labels are kind of interchangeable here. So the probability of B and A is the same as the probability of A and B. So we want to say, what's the probability that the card is red and the card is hearts? Well, that would just be 1 times 1/4, which is 1/4. Okay, the probability of drawing a card that is red and is a heart. I'm sorry, the probability the card is red and is a heart is 1/4. It could be. We could have other scenarios. I don't want to turn this into a thing on Bayes' rule, but you could something be like, the probability, if we're going to travel, okay, and we can say the probability that there's a storm is going to be 1/4, and then the probability that your flight gets delayed if there's a storm maybe is 0.8. Okay, and on the other hand, it might not. It might be delayed even without a storm. And that might happen with only probability 10%. Okay, so we can ask, what's the probability of a delay and a storm? Okay, well, for this to happen, first there has to be a storm, and then on top of that, we have to experience the delay given that there's a storm. Okay, and so the probability of a storm is 1/4.25, and we're going to say, so there's only a 25% chance of there being a storm, and on top of that, our flight has to be delayed on top of that. And so overall, there's a probability of a 0.2% probability of a delay and a storm. Okay, we can ask, what's the probability of a delay and no storm? Okay, so first there has to be no storm, but then still we have to experience a delay given no storm. Okay, so the probability of a storm is 0.25, so the probability of no storm is 1 minus that, or 0.75. And then for us to be delayed with no storm is we still have to experience this delay, which happens only about 10% of the time. So we have a 7.5% probability that there's a delay, even though there's no storm, okay? And so we can do that by just multiplying these out, right? The denominator, just the probability of a delay overall, can be found by combining these two things. What's the probability of a delay? Well, there's two ways that you can get a delay. You can have a delay with a storm, and you can also have a delay with no storm. So we would just add these two together, and that would be our overall total probability of a delay, 0.275, okay? Another way to think of this is that this denominator, probability of B, where we break it up into the probability of B given it B and A and B and not A and everything else, is basically the numerator, okay, which is equal to the and probabilities across all possible values of A. Okay, so that's one thing to keep in mind, is that the denominator is going to be equal to the numerator summed up across all possible values of A. Okay, so we can apply Bayes' rule to make a classifier. Okay, and the idea here is that we've got this training data, X and Y. Okay, we've got all of these observations, they've got these values, and all of those observations have a label. Some of these values belong to category A, some of these belong to category B, and some of these belong to category C. Okay, and then what we want to do is, based on the data that we've seen, if a new observation comes along, we can say, is this new observation part of category A, B, or C? And what is the probability that's in A, probability that's in B, or the probability that's in C? Okay, so you know, we can take a look at some example data, but you know, it might be something like you know, maybe you have measurements on different kinds of animals or something, okay, and you know that, like, on average, you know, your cats weigh on average, I don't know, 8 or 9 pounds, and then dogs of a certain breed on average maybe weigh 25 pounds, and dogs of a different breed maybe on average weigh 40 pounds or something like that, okay? And the idea is, you get a new observation. Let's say a new observation weighs this is an animal that weighs 11 pounds, and this is the only thing that you know about it, okay? And you have to say, is this going to be, what's the probability it's a cat? What's the probability it's a dog of the first breed or dog of the other breed, okay? The medium-sized dogs or the, you know, larger dogs. And, you know, at 11 pounds, most likely going to be just a cat that's a little bit heavy, okay? But that's kind of the idea, that we've got observations. This is like all the different weights and all of their class labels, okay? And then we get a new weight, all right? Maybe the 11-pound animal that we're not quite sure, and we want to say, well, what's the probability it's a cat or a dog of, you know, the medium-sized breed or the dog of the larger breed or something like that, okay? I guess smaller, you know, however we've categorized these animals here. All right. So because the Bayes classifier is predicting a probability, it's always going to be a value between 0 and 1, the result. And then the other thing is that if you look at all the classes that are possible in the model, if you've got 3 different classes, when you add up the probabilities for all 3 classes, they have to add up to 1, okay? And that's going to that's an important part, okay? So if there's only 3 possible options, the probability of being in each of these things, when you calculate them, they all have to add up to 1. If there's 10 different things, the probability across all 10 categories have to add up to 1. Okay, which is specified here. From C equal to 1 to big C, the probability of, you know, whatever, that it belongs to a certain class, that has to add up to 1, okay? So if we apply Bayes' rule here, okay, which is, again, A given B is equal to B given A times the probability of A divided by the probability of B, okay? We're going to call this part the A. The probability of Y nu equal to C, that's going to be the probability of A, given the B. The B is going to be the observed data, X, along with all the training data. We're going to rewrite Bayes' classifier that way, okay? So you can think of this as A given B is equal to B given A times the probability of A divided by the probability of B, okay? The X and the Y show up in the given part because that just means given the training data that we have seen, okay? But you can think of the A and the B as kind of this Y nu and X nu thing. So we'll call this part the posterior, okay? This part is the probability that we get after we do all of our calculations, so it's called the posterior. And this is the value that we want to find. It's the probability that this new observation, okay, that we don't know what class it is. We want to know what's the probability that it is class A. What's the probability that it's a cat versus what's the probability that it's the kind of medium-sized dog versus the probability that it's the bigger-sized dog, okay? So it's this probability is based on the X values of this new observation and all of the training data that we have seen. Over here, this part, the X nu given Y nu equals C, this is called the likelihood, right? This is kind of this is more of like a hypothetical thing that we have to kind of estimate, and we're going to say, well, if we knew that it was a cat, what's the probability that it would weigh 11 pounds? If we knew that it was the medium-sized dog, what's the probability it would weigh 11 pounds? Or if we knew it was the big dog, what's the probability it would weigh 11 pounds, okay? And so, you know, if it were a cat, what's the probability it would weigh 11 pounds? Probably, you know, fairly high. If it's the big-sized dog, okay, where the average weight is 40 pounds, what's the probability it weighs 11 pounds? That's going to be practically zero, okay? You'd have to have some very unusual circumstance where the dog weighs only 11 pounds, and that, you know, that would probably be, you know, concerning. So the likelihood is the probability of getting that measurement if we assumed it belonged to a certain class. Okay. This part, the Y nu given C, Y nu is equal to C, this is the prior, okay? So before we even look at anything in the X, it's just what's the probability that an observation is a cat or a dog or, you know, the bigger dog. This all depends on just, you might have some prior information. Maybe you know that, you know, randomly selected animals are more likely to be cats or something. Or probably you're going to base it off of your training data, all right? And so in the training data, you know, maybe half of the observations were cats, so you're going to just give it and say there's a 50% chance that a randomly selected animal is a cat or something, okay? I'm sorry, these are T's and they should be Y's. Okay, and then lastly, this is the probability of getting the values regardless of class label, all right? And we're going to find this by just taking the numerators, calculating all the numerators across all possible classes, and then adding them up. That's going to be the marginal. So, you know, as far as expanding the denominator goes, okay, we can just say this bottom part is going to be the sum of numerator across all possible classes, which, if we wanted to write mathematically, would be written this way, okay? It's, you know, the numerator, X nu given Y nu given X and Y times this, but we're going to do it across all possible classes. Okay, so we're going to try this silly example of the Bayes classifier. I don't know. I hope it works. All right. Okay, and so the idea is, you know, we've got these pouches here, and so I don't know. Just imagine you've got some kind of pouch, and they're filled with red and blue marbles. All right, and you go online and you order I don't know, 25 of these pouches. You order 25 bags of marbles. And when they arrive, we can see that the bags are filled at 3 different factories, okay? And each of the factories, I don't know, have different proportions of red and blue marbles. So maybe, you know, one factory does more reds and another factory does more blues, and who knows, okay? But anyway, in your data set of 25, 24 of them are labeled, okay? 12 come from factory A, 6 come from factory B, and 6 come from factory C. And then the last thing, the last pouch, is not labeled, and we're going to try to guess the factory that produced it. And we're gonna just kind of assume that the bags are filled with some kind of Bernoulli process, right? Like at factory A, you know, this percentage are red and this percentage are B, and we just take a random sample, and some, you know, some are red and some are B, and some are red and some are blue, and end up in our pouch. Okay, so in our training data, we've got, you know, 24 pouches, and we go through and we count all of our data, okay? And so for, you know, the 12 pouches that came from factory A, we're going to just say 60% of the marbles we observed are red and 40% are blue, okay? So in factory A pouches, 60% are red, 40% are blue. Here's just a picture, a silly picture, okay? 25 pouches. Some we're going to say 24 of them are training data, and we got 1 bag, and we're trying to figure that one out. As far as factory B goes, we're going to say half are red and half are blue. We counted all the marbles in those 6 pouches, and half are red, half are blue. And then we look at the ones from factory C, and 40% are red and 60% are blue, okay? And again, keep in mind, we don't work at the factories, and we don't know the exact filling proportions. So the different proportion pouches that came from the different factories exhibit variation, but we're not worried about it not being part of the binomial process, okay? But you know, overall, the proportions are that, you know, 60% of the marbles from factory A are red, 40% are blue, okay? Whereas from factory C, 40% are red and 60% are blue. Okay, so before we even look at the contents of this 25th pouch that's unlabeled, we're just going to ask, you know, before we look at it, the prior probabilities are, what is the probability that came from pouch A, factory A, B, or C, okay? And so we're going to just kind of assume that our sample of data is representative of the population. And so it might be reasonable to think that because half of our training data came from factory A, that this new pouch comes from factory A with probability 0.5. 1/4 of our pouches came from factory B, so we're going to say the probability that it's B prior to looking at anything in the data is that it's going to be 0.25. And then 1/4 came from factory C, and so prior to looking at anything in the data, we're going to say it has a probability factory C of 0.25. This is our prior probabilities, okay? Now, if you know something, like if you work for this company or whatever, you know someone who works for the company, and they tell you, oh no, all 3 factories produce pouches, equal amounts of pouches of marbles and whatever, then you would put that in here, and you'd say, prior to looking at the data, it should be 1/3, 1/3, 1/3, okay? But if that information is not available to you, okay, that kind of insider knowledge is not available, then it's probably reasonable to say that the proportions that you've observed in your data will hold up for future observations, okay? And that's what we've done here, okay? But again, if you have other knowledge, you can apply that here, and that's our prior probabilities. So this is kind of going back to this. That's this part, the probability that the new observation belongs to a certain class, given all of our training data, is just basically the proportions, you know, how many in our training data belonged to a particular class, okay? Okay, So we open up the bag, okay, and we find 20 marbles. There's 20 marbles there, and 10 of them are red, okay? So in our bag, half of them are red and half are blue, okay? And so now we want to figure out the likelihood of getting this data, right? And so, again, from our training data, we said factory A produces 60% red, factory B produces 50% red, and factory C produces 40% red. Okay, so what we're going to do is we're going to do these calculations, all right? And here we're going to assume a binomial probability, which is, n choose x, p to the x, 1 minus p to the n minus x. And so what this says is the likelihood that it comes from factory A is 60% raised to the 10th, because we got each red marble has a probability of 0.6, and this 10 red marbles that appeared in our bag, so we're going to say 0.6 to the 10. We had each blue marble shows up with probability 0.4 if it comes from factory A, and we say 0.4 raised to the 10, and then we multiply it by, how many possible arrangements are there, and we get a likelihood of 0.117, right? The likelihood that it comes from factory B is higher at 0.5 raised to the 10, 0.5 raised to the 10. So probability of red is 0.5, and that happened 10 times in our bag. Probability of blue is 0.5, and that happened 10 times. So we get a likelihood of 0.176. And then the likelihood that it comes from factory C, so probability of red is 0.4, and that happened 10 times. The probability of blue is 0.6, and that happened 10 times. So that's a likelihood of 0.117. And as we would suspect, the likelihood of factory B right now is the highest, okay? Because when we looked through all of our data, factory A was 60% red, 40% blue. Factory B was 50% red, 50% blue. And factory C was 40% red and 60% blue. And so when we opened our pouch and we got 50% red and 50% blue, that the likelihood of factory B is currently the highest, okay? But what we want to do is we want to combine our likelihoods with the prior probabilities. So what's going on is that before we looked at the bags, we said factory A is most likely because it seems like half of the bags come from factory A and only 25% come from factory B. However, once we opened up the bags, okay, the likelihood of the data in our bag is that factory B is most probable. Okay, so we want to kind of balance this and say, okay, well, factory A has this likelihood and this prior probability. Factory B has this likelihood and this prior probability, and factory C has this likelihood and this prior probability. And so we're going to kind of multiply them all together and kind of compare them, all right? And so what we're going to do is we're going to just multiply this number, 0.117, times the prior probability of 0.5. Okay, so we do 0.117 times 0.5, and we get 0.0585. We do it for class B, 0.176 times 0.25, and we get 0.044. We do it for class C, and we get 0.117 times 0.25, and we get 0.029. Okay, so we are taking kind of the two aspects. One is asking, what's the likelihood of the data that we see inside the bag, and that depends on, kind of our, in our training data, we said factory B is 50% red, 50% blue, and when we opened our bag, it was 50% red, 50% blue, so it seems like factory B is going to be most likely. But we have to balance that with kind of the other fact that in our training data, factory B only produced a quarter of the bags, whereas factory A produced half of the bags. So there's kind of the question: is it more likely that that it came from factory A, where our random sample happened to just have a fewer red marbles than the factory A average, or is it more likely that we got kind of the prototypical factory B bag, and it came from factory B or something like that? Okay, so we multiply these together, and these are the numerator values. Okay, and so as far as the denominator goes, we just take and add up the values of the numerator across all possible cases or classes. So we have 3 possible classes, A, B, and C, and we're going to add them up across all possible classes, and this is going to form our denominator. Okay, so the denominator is just the sum of the numerators across all possible classes. We have 3 possible classes. We calculated the numerator for all 3 classes, and we add them up, and we get this number 0.1319. Okay, and so finally, we're going to just kind of throw in all of these numbers, okay, and get the posterior probabilities. So what is it? The probability that it came from factory A, given that in our data, we saw 10 red out of 20 marbles. And the training data says, you know, factory A looks like this, factory B looks like this, and factory C looks like this. Well, it's the likelihood, the probability of getting 10 red, given that class A has a probability of 0.6, times the probability of factory A, which is 1/2, divided by the marginal, which is getting 10 red regardless of the factories. Okay, and that's going to be the sum across all classes. And we do this and we get the numerator is 0.0585 divided by the marginal, which we found to be 0.1319, and we get 0.0444. We do the calculation for same way for class B. Okay, the likelihood is different and the prior probabilities are different. Okay, and we get 0.334. Okay, and then lastly we get 0.222. Okay, it's just kind of a coincidence that they come out this way. And again, what we're doing is we're balancing out the likelihood of our data. The likelihood says class factory B is most likely, and we're balancing that with kind of the prior probabilities that said factory A was most likely. And so when you combine them all, it turns out that factory A is still the most probable with around 0.44, okay, and factory B is the next most probable at 0.33, okay. So prior to looking at the data, we would have predicted class A with 50% and class B with 25% and class C with 25%. After looking at the data, class A's probability goes down from 50% to 44%. Class B's probability goes up from 25% to 33%, and class C's probability goes down from 25% to 22%, right? And so that is the Bayes classifier, okay? Few things to keep in mind with this is that we used the maximum likelihood estimates for the proportions of red marbles at our factory, right? So we didn't look at all of the training data. I didn't like detail it out, but I just said in our training data, when we looked at all the bags that came from factory A, 60% of the marbles were red, okay? And so we just assumed at factory A, the filling proportion of red marbles is 0.6, okay? Maybe this is not the best assumption, but a little bit beyond our scope, okay? And then, and again, the other part was that because 50% of our training data came from factory A, we just assumed that the probability that our new test case comes from factory A is 50%, okay? And again, if you had other information, you might factor that in and change that, okay? Here's just another example, okay? Same example, different test case. This time, our bag, when we open it up, has 20 marbles and only 6 of them are red, okay? So, so again, factory A says 60% should be red, factory B says 50% should be red, and factory C says 40% should be red. And here we're getting only 6 out of 20, so around 30% in our bag are red, okay? So when we do this and we recalculate our numerators, okay, we get much smaller numbers, okay? The probability of getting only 6 red if the filling proportion is 60% red is very small. The probability of getting 6 red if the filling proportional is 0.5 is small but not tiny. and the probability of getting 6 red if the filling proportion is 40% red is a little bit larger there, okay? And so when we do all of this, okay, factory C turns out to be the most probable, okay? So I just did the numerators really quick, the likelihood times the prior. So the prior probabilities are still 0.5, 0.25, and 0.25, okay? And after we factor all of this in, okay, when only 6 marbles are red out of 20, the probability of it coming from factory A went from, prior to looking at the data, it was 50%. After looking at the data, it's only around 5 or 6%. And basically we're saying that it's very unlikely for a random sample of 20 marbles to have a filling proportion to end up with only 6 red. And so we only get a 6% probability that it belongs to class A, okay? Class B went from 25% down to around 21%, 22%, okay? So it said, you know, it's not super likely to happen. And then class C, which had, prior to looking at the data, was only 25% chance of being class C, now has a 72, 73% chance of being class C, because as far as the filling proportions go, factory C is the one that's most likely to only end up with 6 red out of 20 marbles, okay? Because their filling proportion is something around 40% red, and so it's not that strange to imagine a factory where 40% of them are red produces a bag where only 30% are red, okay? Whereas it's very unusual for a factory where 60% are red to produce a bag that's only 30% red, okay? And so that's what we get. That's the Bayes classifier. Here's another example, okay, of the Bayes classifier where we're going to apply it to a mixture of multivariate Gaussian distributions here, okay? And so the so here we're going to look at some normally distributed data, okay? And it's going to be multivariate. So we've got a normal distribution, but here we're going to just look at it in 2 dimensions. The PDF of this multivariate Gaussian distribution is this mess here, okay? There's some parallels between the regular PDF of the normal distribution for one variable and the PDF of the multivariate Gaussian. Don't worry about this PDF, okay? This is a sigma matrix, and this is the inverse of the sigma matrix, and this is, kind of your vectors x and your mean vector mu, and it's this mess, okay? Let me pull up the Wikipedia page for the multivariate normal. Okay, the kind of the big idea with the multivariate normal is that so here's a 2-dimensional multivariate normal distribution, okay? And the idea is if you look at each variable, x by itself, okay? So here's the x and y plotted together, and it forms like this nice ellipse, okay? But if you look at the distribution of x by itself, it's going to have a normal distribution. If you look at the distribution of y by itself, it's going to have a normal distribution. And if you look at the distribution of x and y together, it's going to form kind of this oval or ellipse, okay? If you plot them together, you get kind of this nice hill-looking thing. So, the hill that you see in a normal distribution appears here. So, if you were to look at it from this angle, okay, it would look just like a normal distribution. And if you look at it from the y side and you look at this way, okay, so just imagine this hill, and if you look at it this way, it's going to look like a normal distribution, and if you look at it the other way from this perspective, it's also going to look like a normal distribution. Okay, and again, just to kind of emphasize that this PDF, as scary as it looks, okay, this thing has a lot of parallels with the regular old normal distribution. So let me just pull up the normal distribution. Okay, so if you look at the normal distribution, what you see is, 1 over the square root of 2 pi sigma squared, okay, and we've got square root of 2 pi sigma here. So sigma squared, this is kind of the variance, but it's technically the determinant, and it's raised to the k power because we're in k dimensions. And then we've got e raised to the x minus mu squared, okay, and we have something that appears like that x minus mu transpose times x minus mu, which, as far as linear algebra and vectors go, this is kind of how you square a vector, is you do x minus mu transpose x minus mu, and we are dividing that by 2 sigma squared, and negative 2 sigma squared, and so we have negative 1/2, and then to get the sigma squared, almost like a division. There's no division in with matrices, but you can multiply by matrix inverse, which is sort of like dividing by a matrix. There's some similarities and parallels there. Okay. Again, I don't expect anybody to like memorize this multivariate Gaussian distribution, but the idea is that this is what we do. We get a PDF. It is in multi-dimensions, okay, more than one dimension, and this will give us our density. And if we integrate this, all right, the total area or volume or hypervolume, if we're in high dimensions, is going to be 1, okay. And so the integral of this whole thing across all possible values of x in its high dimensionality is going to be 1, okay. I think it's going to be easier to just go straight into the example, and we'll take a look at this, all right. And so, sorry, this should say population 1, population 2, and population 3. I've got 3 classes, and I'm gonna just generate data, all right, and we're gonna have data in 2 dimensions, x1 and x2, okay. And so our first one is going to have a mean of 2, 3. Okay, so the mean of x1 is 2 and the mean of x2 is 3. And the variance is 3 of x1 is 3 and the variance of x2 is 1 with a covariance of 0. Okay, we're going to have a mean of 0, 0 with these variances and covariances, and a mean of 2, negative 2 with these variances and this covariance. And to generate this data, I'm going to use this library for R called MVT_norm for multivariate normal. And I can say, give me some random multivariate RMV normal values. I want 30 of them where the mean is 2, 3, and I give it a sigma matrix, okay, which specifies the covariant, the variance down the diagonals and the covariances in the off diagonals. Okay, and so I say XA, XB, and XC. We've got 3 different classes. I got 30 of each, and we're going to just bind these together into some matrix X. And here I'm going to plot them. Okay, I'm going to just plot the values of X, okay, in red, blue, and green. And then also I'm going to draw some contour lines so that we can see this, okay. All right, and so let me kind of move my my window of myself away here, and so here this is what our data looks like. These ellipses represent the distribution that I used to generate the data, okay, and the dots are random values that were produced by this distribution, okay. So we can see, quite a few red dots centered around here, but we get the occasional value that flies out here. Okay, there's some overlap. Okay, here is class B, and they are centered at 0, 0. All right, and the random values that they generated are these blue triangles that show up here. And then the third class, class C, is centered at 2, -2, and there's high covariance between the variables, okay? And so 2, -2 is centered right here, and we can see the high covariance represented by the ellipse that is off at an angle, okay? These black dots represent our test cases. So we're going to try a test case at 0, 0, and we're going to ask the Bayes classifier which distribution does it come from? Does it come from the red, the blue, or the green, right? So if we look at this, we can say, okay, it's going to come from the blue, right? And then here, though, like this test case, does it come from the red or does it come from the green, right? So it's a bit of an unusual point to begin with. And is it more likely to have come from this red distribution, or is it more likely to have come from the green distribution, all right? So that's kind of what we want to know. Here's this test case. We want to know, is it coming from the red or is it coming from the green? And it looks to be a little bit more likely to be green than red, but we'll look at each of these cases shortly, okay? So we generated the data ourselves, so we know exactly where the mean and the variance matrix and stuff, and I'm able to plot these ourselves, okay? But in real life, we only get to see the data. We don't actually get to see what the properties of the population that produces these data. So I think, let me just kind of show the example here. This is what our data would look like in real life. We don't get to see those ellipses. We don't get to see the normal distributions that produce these things. And we just kind of have to estimate them, right? And so on this page, I show how are we going to estimate those parameters, right? And so basically, we're going to just start by estimating the means, right? So the normal distributions are defined by the means and the variance matrices. And so so as far as the means go, we're going to just take the mean of the x values, right? So we're going to just take these dots and the dots that show up in our data and calculate the means, all right? So we just take the column means of x, and we're going to get a mean of 2.267 and 2.82, all right? Whereas when we generated the data, we know that the mean is actually 2, 3, all right? But when we estimate it from the dots that appear in our data, we're getting a mean of 2.26 and 2.82, okay? As far as class B goes, these blue dots, these blue triangles, their mean of our sample of data is 0.3 and -0.1. The actual data is generated from a population where the mean is 0, 0, but we don't know that. We don't know that, right? So we have our training data. We got to just estimate the mean, and we get a mean of 0.3 and -0.1. Okay. Same thing for class C. We don't know how the data was generated. The real data came from centered at 2, -2. We're going to just estimate it, and we get 2.25, -1.9. Okay, kind of close, but not exactly the same, right? Similarly, as far as the variance matrices go, all right, in the original data, our covariance, I think, was variance of x1 was 3, our variance of x2 is 1, and our covariance is 0. And when we estimate that, we use, we're just going to ask for the variance of XA. So XA is, if you keep in mind, there's 30 observations, okay? So the matrix has 30 rows and 2 columns because we've got an X1 and an X2 column. So if you give R a matrix with 2 columns, it's going to, into the variance function, it's going to produce a 2 by 2 variance covariance matrix. It gives you the variance on the diagonals. So the variance of x1 is 2.985. The true value is 3. The variance of x2 in your sample of data is 1.198, 1.2. We generated it from using a population variance of 1. And the off diagonals is the covariance, and in the actual data, that covariance is -0.18. All right, and when we generated it, it was 0. Okay, we generated it, but of course we're getting random data, random values, and so we're not getting exactly what the population says they should be. So we do the same thing. We give XB are kind of our 30 by 2 matrix, and we get a 2 by 2 variance covariance matrix, and we get this, and we do it for C as well. And for the C matrix, that one was the one with the highest covariance. Okay, the true variance is 3 and the covariance is 2.5, and our estimates are a little bit off. Okay, in our sample of data, we got variance of 2.2 and 1.9 instead of 3, and we do see some covariance there. Okay, and so I'm going to plot these contour plots. All right, so using these we can kind of generate our contour plots, and this is what it looks like. So let me just kind of contrast this on page 22 versus the bottom of page 19. Okay, so on page 19, these are the true shapes that we get. So notice there's absolutely no covariance between x1 and x2 in the red, and no covariance between x1 and x2 in the blue. And you can tell that because when you look at the ellipse, kind of the major and minor axes of the ellipse are parallel to the x and y axis, or x1 and x2 axis. And same here, we got perfect circles, actually concentric circles, and so there's no there. And then, you know, we do have covariance here. Whereas when we look at our estimated things, okay, we can see there is slight covariance. Okay, this is the ellipse is kind of at a bit of an angle there. Okay, and similarly the ellipse is at a bit of an angle, and we can see that it's not centered. Okay, our test case is still at 0, 0, and it's our things are not centered at 0, 0. Okay, and similarly this thing shows high covariance, but the lines, there isn't as much spread. If we look at how far the green circles reach in this thing, it kind of reaches farther, whereas when we estimated it based on the data that we observed, it came out a little bit smaller. Okay, and so these are kind of the normal distributions that we've estimated using our data points. All right, and so this is what we are going to use to estimate our likelihoods in the Bayesian classifiers. Okay, I mean, it would be nice if we could get the original things, but that's never the case, right? We're always dealing with data, and we don't know the properties of the population, and so we estimate them. We estimate them using our sample of data, its means, and its covariances, variance covariances, and this is what we have. All right, so you know, it's not centered at 0, 0. It's a little bit off. Okay, and we're estimating a little bit of covariance, not a ton for the red and the blue. Okay, and so we're going to use that to try to figure out what class this test case goes. So we've got, here are 3 test cases, all right, and we're going to try to figure out what class this test case goes to. Okay, and so when we look at this, obviously it should classify. This is just kind of the logic check. You know, is our thing working? It should classify it as case, as belonging to the blue case. So we're gonna take a look at that. Okay, and so just like before, the Bayes classifier is found by doing the likelihood times the prior probability divided by the marginal probability. Okay, so for the likelihood, we're going to use the multivariate Gaussian PDF using the estimates of the mean and the variance that we found earlier, right? We estimated the mean, we estimated the variance of these things using the data that we gathered. We calculated the sample mean, the sample variance, and we're going to use that and plug that in here. Okay, now here I'm doing the actual thing. I'm doing 2 times pi raised to the d over 2, the number of dimensions divided by 2, times the determinant of the variance of A raised to the 1/2 power, all of this. Okay, and it gives me this number, 0.008795399. Okay, this is a pain. I mean, even with R, which makes my life so much easier by calculating the determinant and doing the matrix inverse, it's still a pain to type this. Okay, now thankfully, the multivariate normal package will calculate the multivariate density by doing D for density of the multivariate normal our x new point is the point 0, 0. We give it the mean, which is what we've estimated, x bar of a, which again, kind of going back here, are these values, 2.26 and 2.82. That's our estimated x bar. Okay, we plug that in, and we plug in the variance that we've calculated also, all right? And we give that the sigma, and we say, what's the likelihood? And it gives me the exact same number, 0.008795399. So I don't have to bother with this, okay? And I'm going to do the same thing for class B and class C, the likelihood of class A, the likelihood of class B, the likelihood of class C. And what do we see? We see that for the likelihood of class A, when we say, okay, well, how likely is it to be in the red class? It's pretty low. The likelihood of class B is pretty high, and the likelihood of this being belonging to the green class is very low. Okay, so we're on the order of 0.0087 for the red, so very low. Class B, 0.165, so pretty high. Density for class C is on the order of 10 to the minus 5, very small. Okay. As far as the prior probabilities go, if we look at the proportion in our data, 30% came, 1/3 came from A, 1/3 came from B, and 1/3 came from C. So I'm going to go ahead and just say priors of A, B, and C are all 1/3. Okay. And so the numerators for each of these things will be the likelihood times the prior. Okay, likelihood times prior plus likelihood times prior plus likelihood times prior is going to form our marginal, right? So the marginal is summing up the numerators across all possible classes. We have 3 possible classes. So we're going to take this numerator, the likelihood of A, times the prior probability of A. And we're going to do the likelihood of B times the prior probability of B, and the likelihood of C times the prior probability of C. Technically, because the priors are all the same, I don't, like, they're all going to cancel out when we do the posterior, but just out of good habit, we're going to include them here, right? And so as far as the posterior class probabilities go, we do, following Bayes' rule, the likelihood times the prior divided by the marginal. I'm going to do the likelihood times the prior divided by the marginal. Okay, the likelihood of A times the prior A divided by the marginal, likelihood of A. And what we get is we get that it belongs to class B with probability 0.994. It belongs to class A with probability 0.005, and probability of class C practically 0, okay, 10 to the negative 5 on that order here, so very small. So around 99% probability that it belongs to class B, all right, and so very very high probability there. All right, let's take a look at this one, okay? So when we look at our data, and again, we don't know the actual distributions that generated this, and so we've only estimated these, right? So using our estimates, what is the probability that it's going to belong to class A or the green class, okay? And so this one looks to be a little bit more likely to be A, and maybe green, and very unlikely to be blue. All right, so this test case is at the coordinate 6, 2. So I'm going to say x new is 6, 2. And we calculate the likelihood using the density, right? DMV, density of the multivariate normal of our new point, 6, 2, using the estimated mean and the estimated variance for class A, the estimated mean, the estimated variance for class B, estimated mean, and estimated variance for class C. So these are our estimates based on the data, okay? Because we don't know the real true values. These are the estimates. We plug in the priors, which for all of these are 1/3, and we calculate the marginal, which is the likelihood times the prior. That's the numerator for all possible classes. Likelihood times prior for A, likelihood times prior for B, likelihood times prior for C. And then the probabilities that we calculate will be the likelihood times the prior divided by the marginal. That's Bayes' rule. And so what it says is that we have around an 80% probability, 79% probability that it belongs to class A, and around a 20% probability that it belongs to class C, and something very close to 0 probability of it belonging to class B, the blue class. Okay, which which matches what our brain would tell us when we look at this picture. Around 80%, close to 0, close to 20%. Okay, and so this is the Bayes classifier in action, and it does a very good job. And in these diagrams, I've been doing two-dimensional cases, but it easily expands to higher dimensional cases as well. All right, here's our last test case. It's at the coordinate 5, 1 right here. And we're going to just kind of do the same thing. Calculate the likelihood using our estimated means and variances. Not the actual ones, because those aren't available to us. We estimate the mean, we estimate the variance using, the data points that we've gathered. And when we do this, it says it's around 39% belonging to class A and around 61% probability of belonging to class C, the green one. So 39% belonging to the red class, 69% belonging to the green class, and close to 0% belonging to the blue class. Okay, again, because the density, the probability of it, that the blue class produces something way out here is very, very low, and that's what we get. So that's the Bayes classifier. All right. So now I'm going to talk the naive Bayes classifier. So the naive Bayes classifier is very, very similar to the Bayes classifier. The big distinction with the Bayes classifier and naive Bayes classifier is that the naive Bayes classifier makes what we call the naive assumption. And it is going to assume that all of the predictor variables in X are independent of each other. Okay? All the predictor variables in X are independent of each other, which in our case means that when we make our predictions, we're not going to have any covariance between the X1 and X2 variables. So here we have high covariance between X1 and X2. And when we do the naive Bayes classifier, we're going to assume no covariance. We're going to get basically, when we form our ellipses, they're going to have the axes of the ellipses will be parallel to the X1 and X2 axes, and they're perpendicular to each other. That's going to be a bad assumption in a lot of cases. Okay, in a lot of cases, the X variables will have some kind of covariance or correlation between them, and the naive Bayes classifier explicitly says we're going to assume that there's no covariance, no correlation, and we might say, well, why would we do that? Why would we purposely make a model with a bad assumption, with an assumption that we know is bad? Okay, well, it turns out that even though it's a bad assumption, sometimes you get better performance. Okay, how can that be, right? How can I get better performance if I'm using a model that's explicitly worse, or like makes an explicitly bad assumption? Well, what happens is that the amount of values you need to estimate decrease a lot. Okay, so in the in this thing, when we estimated the parameters, okay, we had to estimate the mean of, for class A, mean of X1, X2, mean of X1, mean of X2, and mean of X1 and X2 for class C. Okay, so there's 6 means to estimate there. And we have the variance and the covariance. So we had a whole bunch of these values to estimate. And with the naive Bayes classifier, we don't have to estimate any of those covariance values. And if you have a bunch of X values, okay, X variables, like 4 of them or something, there's going to be 4 mean, 4 variance, and 6 covariance values to estimate for every single class. Okay, so if you have 3 classes, you've got to estimate 12 means, 12 variances, and 18 covariance values in total. That's a lot of values. Okay, that's a lot of values to estimate. And if you don't have that much data, your estimates might be like wildly off. Okay, your estimates could be really far off if you don't have that much data to begin with. And so it could end up performing poorly, all right? So the naive Bayes classifier just says, you know what, let's just say everything is zero. All the covariances are zero. We don't even have to bother estimating those, okay? And that's saves us from some trouble. You're going to get bad performance if there is high covariance in between two of the x variables. And so this is where kind of your knowledge of the data will play a role, all right? And I always emphasize that you can't just take a machine learning algorithm like the naive Bayes classifier and just say, let's just throw it at some data without understanding anything about the data, right? When you understand the data, you can say like, oh, I know that these two variables are highly correlated. Okay, the naive Bayes classifier is going to do poorly if two variables are highly correlated and you use the naive Bayes classifier and you say they're not correlated at all, right? The naive Bayes classifier does well if there's only a little bit of correlation between some of the x variables, right? So as far as like if you have a housing data set, you probably know that the number of bedrooms and the square footage of the house are going to be highly related, okay? And if you include both of those in your thing and you use a naive Bayes classifier, you're going to get not so great performance because you've got two variables that are highly correlated and you're explicitly saying that there's no correlation. What's going to be better is if you just keep one of them and you throw the other variable out, right? And you just say, well, let's just use square footage of the house, okay? And I'm not going to use this other highly correlated variable in there, okay? Or you use the Bayes classifier and just say, well, let's try to estimate the covariance, okay? So the knowledge, your background knowledge of the data is always important because it's going to inform you about whether some of the assumptions that are going into this thing are reasonable or not, okay? If it's reasonable it is reasonable to say, the correlation between these two variables is going to be small, so it's going to be okay to just zero it out, right? That's probably fine, right? But if you know that things are highly correlated and then you insist on using the naive Bayes classifier, that could get you in trouble. So anyway, how does this work? Okay, well, it turns out that it's going to be quite easy, right? If you struggled, right? So thankfully to R, we were able to calculate the multivariate densities very easily. We didn't have to bother with this crazy PDF using matrix notation. We were just able to use R's multivariate normal function. We just say dmv norm and R did it for us. Okay, with a naive Bayes classifier, this isn't a concern. We just use the univariate thing and we just say, well, because everything is uncorrelated, we can just take the product. Everything's independent. The product, the joint probability of two independent events is just the product of their probabilities. So again, here we're going to just kind of revisit this one example where the test case is right here at 5,1, okay? And so with the naive Bayes classifier, we just estimate, okay, what's the mean of x1, okay? And here, like I could have used the same things that we did before, but here I just say, okay, we're going to just take each variable individually. We're going to take the mean of, so x1 bar, okay, the mean of x1 for class A is just going to be the mean of xa for column 1. X2 bar for class A is the mean of xa, column 2, and I do that. And then as far as the variance values go, I'm just calculating the standard deviation of each column individually. All right, so these are all the values I have to calculate. I need one mean, two means, okay, x1 and x2 bar, and two standard deviations, S1 and S2 for each of the three classes. So there's a total of 12 values to calculate, okay? And it looks like a lot of stuff going on here, but effectively I'm just taking each column one at a time and calculating the mean and standard deviation of each of them. So I'm just taking, column 1, standard deviation for class A, column 2, standard deviation for class A, column 1, standard deviation class B, column 2, standard deviation class B, okay, so on and so forth. I just do that for all of the classes and all of the variables, but I'm just doing them one at a time. There's no covariance for me to estimate, right? And then as far as the densities go, they're just going to be the product of two univariate normal densities, and you can kind of see that when I calculate the contours. But again, the result is that the contours show no covariance. These are the axes are parallel to the x1 and x2 axis, and the major and minor axes are perpendicular to each other. You don't have any ellipses that are kind of at an angle. They're exactly all horizontal and perfectly vertical as far as the major and minor axes of these things go. So we can see that for this case where you have high covariance between x1 and x2 for the green, it's not so great, okay? In your next homework, you're going to do the naive Bayes classifier for the IRIS data set. And some of those variables exhibit covariance, but you'll see that the performance of the naive Bayes classifier is still pretty good, even though there is a bit of covariance between them. It's just when you have very high covariance between some of the variables, then the naive Bayes classifier, it's not the greatest, okay? All right, so let's go ahead and do calculating the class probabilities of this thing, and we're going to do likelihood times prior divided by marginal, okay? And so as far as the likelihood goes, look what I do. So our test case is at 5, 1, and I say then our likelihood for belonging to class A is this is the regular univariate normal density, D norm. There's no MV. It's just density, normal density, D for the normal. And I give it one value, the 5, and I give it the mean for class A and the standard deviation for class A. And then over here I have the other variable, okay, has a value of 1, and we give it the univariate normal and the mean of x2 and the standard deviation of x2, x2 for class A, and we take the product of those two things. So we have two normal densities that are univariate, so one variable at a time, and we just take the product of them. And if you had 4 variables, okay, you would do 4 univariate normal densities, so normal density of one variable at a time. You do it for all 4 of them, and you just multiply all 4 together. You are not going to be doing the multivariate normal where you're taking all 4 and you need the covariance estimates of all of those things. Okay, so the likelihoods are calculated this way by taking the product of 2 normal distributions one at a time. The prior probabilities are all 1/3 as before, and so the marginal is going to be the product of all of these things. Okay, and so here I take the likelihood times the prior divided by the marginal, likelihood times prior divided by marginal, and here we get values of around 80% of class A and 20% class C. Okay, so according to this, there's a 80% probability it belongs to class A and around a 20% probability that it belongs to class C. If you compare that to the regular Bayes classifier, the regular Bayes classifier was closer to around 40% and 60%. So 40% class A and 60% class C. So our values are a bit off here, and it stems from the fact that we're estimating no covariance in the green case here. Don't let that turn you off from the naive Bayes classifier. This is a kind of an extreme case. If you try out the naive Bayes classifier in many other situations, it has actually very, very good performance. And And a neat application is you can use like the naive Bayes classifier for document classification. You just treat each word appearance, the probability of a word appearing as being independent of other words appearing, which is not the case. We know that when we speak languages, certain words are more likely to appear together than other combinations. But if you look at each word, there's like hundreds of thousands of words, and you would have to calculate the covariance of every single word appearing, and there's just way too many, right? What's the covariance of the and a showing up, and the and phone, and the and computer showing up together, and a and computer and phone showing up together, and there's just way too many covariance values to calculate. It's not going to be possible, and so the naive Bayes classifier eliminates all of those covariances that you have to calculate, and you can do document classification. I'm going to put a break in the video here. We'll come back and we'll take a look at k-nearest neighbors. Hang in there. I know it's harder watching the videos than it is to sit in person, but thanks for tuning in, and I'll see you right after the break.